Hello all! In this video, we're going to be showing, using epsilons and deltas, why the function f of x equals x squared from r to r is continuous. So, like all good epsilon-delta proofs, I'm going to start off my proof by saying let epsilon be greater than 0. I also, since I'm trying to prove that this function is continuous on r, we don't have a specific point we're trying to prove it's continuous at, I'm going to let x be any real number. We're going to want to find a delta so that whenever our inputs are within delta of one another, our outputs are within epsilon of one another. I don't know what that delta is going to be yet, but since I'm going to be delving into what the function itself does, I don't need to establish any deltas earlier on. I'm just going to say take delta equals, leave this blank, and fill it in once things become more clear. So, what we were trying to show, this is my scratchwork column over here. So, given our delta, we want to show that if we've got some a that's within delta of x, then f of a and f of x are less than epsilon apart. So the distance from f of a to f of x is less than epsilon. Since this is an if-then statement, I can assume the if part of this. So I can say we'll assume that we'll pick an x so that the distance between a and x is less than delta. We don't care about any other values of a. And in this case, since we're talking about distances in the real numbers, we can say absolute value of x minus a is less than delta. So now I want to figure out how we can show that our distance between our outputs is going to be less than epsilon. So I'm going to start off with distance between f of x and f of a, which in this case will be the absolute value of f of x minus f of a, or sorry, I should keep symmetry here. F of x minus f of a. Even if we were to have flipped those, it wouldn't change the ultimate proof. So we want to figure out where we can go with this. We know what f of x and f of a is. We might as well translate that. X squared and a squared. We want to relate this back to x minus a because that's what we've got information about, absolute value of x minus a. I can rewrite x squared minus a squared as x minus a times x plus a. And then you can split up absolute values over multiplication. So this would be x minus a, times x plus a. This bit here we know is less than delta. So we would want to figure out some way of taking this scaling, whatever our delta is, it's going to get multiplied by x plus a. That's a little bit awkward because we chose a after we chose delta, so we've gotten ourselves into a circle. We need to replace this thing here with something that doesn't involve a, only depends on x and various constants, known numbers, so that we can rewrite things, choose our delta, and then choose a based on our delta. So we've got this idea. We know that we've got our point x here. We've got the interval x minus delta and x plus delta. A is in this interval somewhere. We want to figure out some way of, putting some sort of bound on x plus a. We know that x plus a by the triangle inequality is going to be less than or equal to absolute value of x plus the absolute value of a. So we need to get the absolute value of a itself somehow to be related to x. We know that a is going to be within x minus delta and x plus delta of x, but we need to figure out how to turn that into a concrete inequality. There are going to be two steps that we'll do. First, this x plus delta, x minus delta range, we could say that x and a are pretty close, so x plus a isn't going to be too far off of 2 times x-ish. It'll be pretty much something like x plus x, but how far off? We're going to need to take whatever correction is there into account. We know how far off is no less than delta, but we need to define delta in order to here define delta. So let's give ourselves a slightly more concrete thing. We're going to say that whatever delta is, we're going to decree that we want it to be less than 1. So the minimum of 1, and we'll take delta to be the minimum of 1 and some other thing. The some other thing will be what guarantees that we're within epsilon, but this saying that delta, we want it to be at least no larger than 1, will help us be definitive about something so that we don't define things circularly. So now we know that the distance between x and a is going to be less than 1. We'd sort of like to say, with this picture here, where it looks like, x is positive. If we say that x is positive, a is positive, certainly a is less than x plus 1. But if everything were flipped, things were negative, it could be that the absolute value of a is no greater than the absolute value of x minus 1. There are a few too many things that could flip depending on how x, a, and 0 are positioned relative to one another, that we need to be a little bit careful. We can, though, take this statement here and try to rework it using something that's known as the reverse triangle inequality. As I'm looking at this, I think I am going to flip and say that this means that a minus x is also less than 1, just to make our lives a little bit easier. So anyway, I'm going to use something that's called the reverse triangle inequality, a way to get at doing something like the triangle inequality, but preserving this x minus a bit to a certain extent, or at least preserving the fact that the information that we've got is about the distance between x and a. This isn't quite the reverse triangle inequality either, I don't think, but it's going to feel a little bit like it. I'm going to add x to both sides of the inequality that a minus x is less than 1. You can add anything to both sides of an inequality and have it stay true. It's multiplying that we need to think about, whether you're multiplying by a positive or a negative number, whether the inequality should stay or flip. So anyway, I've added x to both sides. That's a thing that I can do. This side here on the left, I see that this is thing plus thing. The plus is outside the absolute values. Triangle inequality says that if the plus were inside, the inequality will only get potentially smaller. So if I rewrite a minus x plus x here, this thing is less than or equal to what I've underlined in blue, the a minus x plus x, and then we know that that is less than 1 plus x. This piece over here is the same thing. The x's now can cancel. So this simplifies down to the absolute value of a. And then over here on the right, we have that that is going to be less than 1 plus x. So now I have replaced this the direction that we want to go. We know that this is going to be going back to our regular proof, and I'll get rid of these extra things in green because they aren't going to be part of the formal proof. Anyway, so this is less than or equal to x minus a times, we know that the absolute value of x plus a is going to be less than or equal to the absolute value of x plus the absolute value of a. And we've, by our scratch work over here, shown that that is going to be less than, actually it'll be strictly less than x minus a times absolute value of x plus the absolute value of x plus 1, replacing absolute value of a with that piece. So we can rewrite that bit as the absolute value of, x minus a times 2 absolute value of x plus 1. The x minus a part, as we said, is less than delta. I'm seeing here that I'm multiplying delta by 2 absolute value of x plus 1. So if I take delta to be epsilon divided by 2 absolute value of x plus 1, things will cancel and I'll get what I want. So if I say that delta at least is equal to the minimum of 1 and then 2 absolute value of x. Sorry, that's not what I want. I said I wanted to have epsilon divided by 2 absolute value of x. And then as epsilon gets smaller, this will get smaller. We know that we want to make sure we're never dividing by 0. Also that this isn't ever going to be negative, but 1 is going to be strictly positive. 2 times the absolute value of x isn't ever going to be negative, and so, sorry, this is always going to be greater than 0. So we're good. This is an applicable delta. And so we know that delta is going to be no larger than epsilon over 2 absolute value of x plus 1 here. Things cancel like we want them to. And we've gotten, finally, that f of x minus f of a is less than epsilon. So that's more or less the end of the logic part. I will just finish off my proof with the sentence that f of x is continuous on the real numbers as Thank you for watching, and enjoy your epsilon delta proofs.